runs one of the other New York City Haskell-based startups, and he's going to tell us about using big data with Haskell.
Sounds good. All right. Hey guys, my name is Oz. I think last time I presented was maybe a year and a half ago. Let me get in front of the computer. So today, I guess I'm going to talk about Hadoop and Haskell with a couple of objectives. One is just to show you guys a library that you can actually use to, I guess, construct MapReduce programs on Hadoop. And second, it's sort of a case study of, quickly bootstrapping a library in a pinch, if you will. For this, we didn't have that much time. We were under some deadlines, and we still wanted to use Haskell for some reasons that I'll talk about. And so it actually came together pretty nice. We've gone through several iterations. There's a lot to improve on it for sure, but I think it still makes for a pretty good case study. So firstly, if you feel like it or want to check it out, it's actually now open sourced. It was a private repository up until today, but now it's actually public, so you can go and check it out. Just a little bit about us. So we're a company using Haskell for pretty much everything. Just thinking about all the different things we do. We have web servers, pretty high volume APIs running on Haskell. There we use snap, heist, digestive functors, and some other libraries that we developed. We use databases, obviously, as a real-world sort of company. We use a lot of Postgres. Recently, we've started using Groundhog for it. We use Cassandra for one of our big data stores, Redis, and we've probably tried a few others, but these are the major ones. Pretty much everything for us is on the cloud. We have been using Amazon. It has pluses, minuses, but I think in the end, it's pretty convenient with all the different services that they offer. We use Haskell for machine learning and analytical models. A lot of times, we might maybe prototype by hand on either other languages or maybe platforms that may exist, things like MATLAB or whatever. But in the end, for something to go into production, for us, it ends up being written in Haskell. We do a lot of data logistics, pre-processing, analysis, and lately, a lot of visualization directly on Haskell. So that's been very interesting. Incidentally, we have a lot of DSLs that we've developed in-house. Anything from actually generating SQL queries using sort of a more principled expression, let's say language, to some custom selector-like queries that we have for our internal systems. We have quite a bit of it. We do crawling to collect some data from the web. All that, again, happens on Haskell. And recently, we've been really thinking about and sort of planning for generating JavaScript through Haskell. So we have some in-house JavaScript code that quickly for us got out of hand, and so we are very serious about converting to Haskell. Now, in the middle of all this, we do a lot of data analysis, obviously, and there came a point where we needed something like Hadoop because the data was large, and we had to do some decent processing on it, some long pipeline, and there was no way to do it on Haskell. So, after looking at the options, we ended up creating it. So that was, I guess, the motivating factor for this library. So just a word on Hadoop. Maybe everybody here already knows it. But just for me to know, how many people here have worked with Hadoop before? All right, maybe 40%-ish, seems like. So this is probably old news to everyone, but it's actually a very powerful platform. Recently, there's been all kinds of new sort of databases and real-time systems. That's true, but Hadoop still is pretty powerful, especially when coupled with something like the Amazon Web Services. You can spin up, say, 300 nodes within 10 minutes, actually crunch through a lot of data and shut them down. This is pretty nice. And in the end, maybe the speed up you get is not really linear. So maybe 5 nodes are not strictly fast, 5 times as fast as just the one node. But in the end, you really get massive parallel operation, and it really makes things faster. And then you really feel pretty cool because you have 500 machines all working for you. It's kind of a nice thought. So I guess what is already available in the market, because we're not just having fun here. We wouldn't create the library just for no good reason. And so there's a few options. I mean, there's much more than this, but just to go over them quickly. So Hive is a way you can use Hadoop to run SQL queries. It works really well But obviously, wherever SQL itself becomes hard, that's exactly where you start having problems with Hive. So if you have some custom data or data that's not really well structured and it's a pain to get it into that nice tabular form, that's when Hive is not that convenient to use. There's Pig. I mean, we haven't used it in any sort of detail, but it just looks like it's almost like a custom DSL that you kind of have to learn anyway. And so I guess that's what that is. And then, for example, there's the whole cascading, scalding, Cascalog sort of group of, I guess, infrastructure. They're Java, Scala, I believe, and then Clojure. I guess the big problem here is that they're not Haskell, if you like to use Haskell. And then in the end, they're very DSL-like. So either you go to cascading and do it in Java and actually construct the full program in Java, or you end up learning some kind of a data log style DSL in the end. And so you kind of go back to the Hive argument where, I mean, if you can do it in SQL, then you might as well do it there because it's pretty good. So we wanted something that would give us Haskell on, for MapReduce programs. I'm not going to go into any detail. I think it's obvious to everybody what strong typing, advanced type system, first-class functions, purity, quick check. I mean, there's many benefits. Another one that often comes up is, if you do a lot of Haskell, you have your data type definitions in Haskell. You produce data records that you might export as JSON or maybe sometimes even save as safe copy instances. And all these things already have serializations defined for you in Haskell. So if you now go try to use Hive for this, you're going to have to duplicate the definitions in SQL, and it's just painful. And a lot of times you might actually make errors. As your code evolves, those definitions are not going to evolve with the code, so you duplicate effort now to maintain things. So it's just not very convenient. And then the other thing is, if you have a long chain of MapReduce programs, so sort of you have one program that produces some output, another program uses that to produce some more output, and then you maybe join the two and do other things, the more complex it gets, the more you benefit from something like Haskell, where you get pretty strong guarantees and good reasoning about the program that you've just created. And then we wanted something that would work really well with the Hadoop ecosystem, kind of wrap around things that are not a lot of fun to do yourself. And like I mentioned, we definitely needed to work with different data formats in a nice sort of smooth fashion. So CSV files, maybe serialized instance, marshaled log files, JSON, other proprietary binary formats. It's all the same. Okay, so a place to start for those of you who may not know Hadoop that well. Hadoop has this, what they call a Hadoop Streaming interface. It's kind of an escape hatch to be able to use arbitrary binaries on Hadoop. So basically, a Hadoop system, you probably have, let's say, for the sake of argument, you have 50 nodes. You have one master node that's sort of managing all the 50 nodes. You can have an executable. You tell the master node, please run this program for me as a MapReduce application, and then that master node will ship the binary to all the remote nodes and get your code running on all of them. But I guess there are some difficulties in the process because the way Hadoop Streaming is designed, it expects that binary to work with new line separated stream of input, and it expects a new line separated stream of output from it. And then on each row, it expects sort of like tab delimited fields, and there's some other details too. It's just not very convenient to work with. And to top it off, this is how you call it for a single MapReduce application. So you craft all your application and then you want to run it. It's just one MapReduce cycle, and this is all you have to type, and you have to get everything right. So you have to know your separator fields and how many sort of segments you use, and where you put your executable, where the input file is, where the output file is. I mean, obviously it's very error prone to do this, and it's just very low level. So I guess before we started, we also took a look, what have others done to battle this problem. So there's, for example, this is a very common tutorial that, it's funny because I saw this maybe a year and a half ago, and I still see it as the top link when you search for it. So I guess it's a good blog post. But basically, it's vanilla Python, so there's no framework, no nothing. When you look at the program, the first thing is that it's not Haskell. So it's very extremely imperative. It literally goes line by line, reads from standard in, strips the line, separates the tabs, figures out if it's good or not, and then does its thing, and then sort of emits the result. And then even at the very bottom, it says, don't forget to emit the very last one. So it's very, very imperative in the way that it works, because it ran through the whole input, and then maybe input just stopped, so that it has to be smart enough to remember remember to push the last point. So basically everything is left to the user here. You handle input, you handle output, you handle parsing, you handle new lines, and everything. And so the question is, I guess, what if you have to run 4 of these things? I mean, it gets very, very complex very fast. Obviously, which is why on Python, for example, people have created abstractions around this. So nothing to, I guess, say anything bad about these solutions, but I guess for us, they're still not Haskell. We would like to create something on Haskell. There's still the whole, you create a class for each job, so you have multiple files. There's still the complexity of running these programs, so you still have to really tightly manage, run one, then run the next one, then run the next one. Maybe not very composable in that sense. Okay, so switching gears a little bit, how would we do this for I guess, Haskell? Well, if we look at the big objectives, first we would want to wrap around Hadoop really well. So we want to parse the input stream pretty well, handle the new lines for, I guess for the users, and just kind of take care of all the low-level aspects. Then we would like typed input and output. So as we write our programs, I don't want to say, here's an incoming stream of byte string, and here's what to do with it. But rather I would say, if my data is an incoming stream of, let's say, hits on a website, for example, then I want to say, I just took a hit, and I did this thing, and then I spit out maybe some kind of analysis result. So I want type safety in my input and output. Now, once I have that, I want to construct my MapReduce program in a type-safe way, and it needs to feel like Haskell as we craft it. And then finally, we would like to be able to use all the nice Hadoop things, like Hadoop file system, which gives you, you can write something into that file system on the master node and then read it back on any of the remote nodes. I mean, it's a pretty nice central coordination system. So this is where we'll start showing some code. I guess, apologize, it's a lot of text, but I just wanted to show some content as well. Obviously, just stop me and raise your hand if something doesn't make sense to you. So when we first did the lowest level implementation, we started with, typical sort of type-driven design. What is a mapper? What is a reducer? And, here's the general idea. As the input comes in, you want to be able to say, okay, I take row by row, then I reserve the right to maybe collect a few of those, and then, when I'm ready to emit, I'd like to emit a key value pair. I might take a row, and I might emit 10 rows from that. I might take 50 rows and I might emit a single row, or I might take everything and decide that I'm not going to emit anything. So essentially you need a pretty flexible way to decide, for each input what you want to emit. And so just because of its ecosystem and it kind of has this concept built in, we ended up using the conduit library. I have some comments. It's actually not always it does give you some headache sometimes. It has weird asymptotic behavior when you least expect it. If you chain conduits in a certain way, your program will just sort of stop running at some point. There's some unfortunate things about it, but by and large, in 99% of the programs, it'll work very well. So what the conduit buys us is this type signature here basically says that the conduit takes input items of type A. It's constructed over the I/O monad, so you can actually do whatever you want. And then it emits a key value pair, essentially a key type K and a value type B. So this is our mapper. So pretty much like a generalization of the simple take something and emit something kind of pattern. Then our reducer basically takes a key type K and inputs the actually item type A, and then it sort of, I guess, eats through those, and at the very end, it decides to emit a result type of R. I apologize, it's a little unfortunate here. Essentially, the K-B pair here is what the reducer takes as input. So whatever is the output from the mapper becomes the input to the reducer. That's how how you should think about it. Now, obviously, the cool thing with Hadoop is that this doesn't happen on the same physical node. So you might have 50 nodes that do the mapping, and then all those results will get shuffled over the Hadoop cluster, and then reducers will run on additional reduce nodes. So essentially it's parallel computation, and all of that is done for you by Hadoop. We have some details, certainly some MapReduce options that you need to communicate to Hadoop. Nothing to go into detail here, but just to note that there's a few choices you can make as the programmer. And then in the end, at this very lowest level, what you can have is, let's say, a MapReduce combinator. You pass to it your MapReduce options. You pass to it a prism, which essentially is a serialization strategy from the lens library, incidentally. A prism basically is something in this form. It basically says that it can translate an incoming, let's say, byte string blob into an A, and then it knows how to go back from A to a byte string. So it's essentially an encoder coupled with a decoder. It's just a convenient way to think about it that way. This is important because that's between the map and the reduce stage. We're going to take the Haskell type A, we're going to turn it into byte string, and then it's going to be shuttled off to the nodes that are going to do the reduce, and then it's going to be unpacked back into the A type, and then it's actually going to be reduced. So you kind of pass that in. Then you give it a mapper, you give it a reducer, and it gives you two I/O functions. You can execute essentially a mapper function and a reducer function. If you were to run those, then your map and reduce run. Seems good, but the big problem is that it's still very, very low level, right? I mean, it's only for running a single MapReduce program. You still have to deal with that ugly Hadoop command line call. The development cycle itself gets annoying. Like, it'll run once, but the second time you run it, it'll complain that the destination file already exists. So you have to go by hand delete it, come back, run the program. Gets pretty annoying. And then you really by hand have to make sure all the input-output, everything just sort of fits right. And then the other really downside to this is, if I were to bring this up again, you'll notice that in our mapper and reducer types, like everything is byte string based. So this is basically saying that I'm expecting blob byte string input, and then at the end of the day, I'll give you a blob byte string output. So we have essentially no type safety. So you could think that if you forget, if you make a mistake, you could be writing like JSON into a place where you hoped you would be writing a CSV file. And there's really nothing to stop you from that. And it takes a while to sort of find these bugs. So the question is, can we build something on top of this to sort of make this a bit smoother? The first thing, I guess, to do is to solve this input-output type safety problem. So I guess our approach to this, we wanted something that was easier to sort of reason with, not super complex, but still something that gives us some structure. So we defined a protocol type. A protocol type is basically a pair of conduits. So it's something, it's a record, obviously. It knows how to turn type A into B, and then it knows how to turn B back into A. This is kind of like the lens prisms, but they're both conduits, which basically means that they operate over I/O, so you can do arbitrary conversions, and you can even handle things like the input file might be binary, so you might be just decoding something that's even very, very complex. So it gives you enough freedom to do whatever you want. Then we define a protocol prime type synonym, which essentially encapsulates the common case where your underlying data is byte string, but you're giving meaning A to it. As you take it, you parse it. We can define a category instance to this, which is nice because then you can compose multiple protocols. So you can start with something that converts byte string into, let's say, type A, and then you can chain another conversion from A to B. So it's very nice. It becomes very compositional. And we also come with some sort of out-of-the-box protocols. ID protocol is a simple one. It's just ID, so it leaves byte string as is. Lines protocol just parses new lines for you. So it spits out one byte string line at a time and makes it slightly more convenient. Then we have this base 64 serialized protocol thing that we defined. What this does is it first takes ID protocol, then let's go the other direction. It takes a Haskell object, it turns it serializes it using the serial library, then it base 64 encodes it, and then it sort of chains lines protocol to convert it to a new line terminated stream of essentially byte string blobs. Why? Because Hadoop is really particular with new lines. If your data itself has new lines in it, it trips up because it sees new line as something that separates multiple lines. So if you have a binary blob, say an image, it really can't have any new lines in it. So our solution is for almost everything. Internally, we use base 64 encoding, and it works pretty well. But we also have things like, we can unzip, for example, data files. We can, read in CSV files. We can even, output something with Haskell's show instance and read it back using the read instance. All of this just very naturally works. And as soon as we have this, as I'll show you in the rest of the framework, now we can start working with actual typed input and output. We don't have to anymore deal with byte strings ourselves. Okay. So this is probably the ugliest slide we have. So now we have typed input, and we've had a bunch of low-level problems before. Essentially what we want at this point is, or at least one of the good solutions to this problem is, imagine having a monad, so some kind of a monadic interface, and let's say you have a chain of 7 MapReduce programs. It would be nice if you could essentially take, the first MapReduce program, connect its input, connect its output, have it run, and then have another MapReduce program, maybe connects its own input, connect its own output, and even maybe have a third one that takes the output from the first one and the output from the second one, and then generates its own output. And you would like to be able to run all this as a sequence of events, as a sort of a self-contained pipeline, if you will, of MapReduce programs. So one way it occurred to us at the time to do this would be the free monads. I guess in the interest of time, we're not going to go through and explain everything about a free monad, but there's a library on Hackage called operational. It's one of the free monads, I guess, or a variant thereof. And it takes care of a lot of things for you. Essentially what you do is you define the distinct primitive operations that your interface is going to be allowed to do. So in our case, our interface, defined by the con-I type, the con stands for controller, it will have, we said it will have the ability to take a MapReduce program and connect it to what we call a tap. And notice, maybe I should have explained this first, a tap is simply a protocol and a number of file locations. So this is like saying, my input resides in these files, and as you're reading it in, use this protocol. So it kind of encapsulates a file location together with the protocol that you're going to use to decipher that location. So going back to our controller, so we have a connect instruction. It takes a MapReduce program. It takes a list of input locations. It takes an output location. And it takes a name. You can name it. Just in reporting, it looks better. And that's it. That's basically all there. So it's the instruction that connects a MapReduce program with a bunch of input files and an output file. So that's great. That's our instruction number 1. Now, instruction number 2, in the course of running our programs, we occasionally want to create temporary file locations. So, and that's what the make tap instruction is for. You give it a protocol. This protocol could be, again, maybe a serialized protocol. So it's something that knows how to convert from byte string blobs to Haskell types through the serialized interface. And then it gives you a new tap that you can then use in the rest of your program. So it's, in a way, it's sort of like make temporary file, the equivalent of that in the controller monad. We have a special case for binary dir tap. Now, this is more complex, but the main purpose of this is, imagine you have, I don't know, 100,000 images on Hadoop or Amazon's S3 that you want to encode. And you want to use Hadoop because you want to have 50 nodes do it for you. I just explained that Hadoop is really bad with new lines. So if you try to just read that in, it will just mess up and it'll get stuck, it'll raise errors. So what we do instead is we have this combinator here. You can give to it basically a file path that tells you, here is where all my files are located. Here is a filter function in case you want to, exclude some of those files. And then it will do some intelligent things behind the scenes to give you a tab that can read that cleanly. So it will sort of wrap around that whole binary problem, and it will actually give you the contents of it in a very clean sort of fashion. We have one. We can do I/O. So this is obviously, you don't want to do I/O, and you don't want to base your decisions on the result of this, because I guess maybe one thing that's coming up, and I'll show that in more detail, but anything that you do using these primitive operations will run both on the master node and all of the remote nodes. So if you say something like, do some complex I/O and put a logging statement for me, that's a little dumb, because it'll run on the master node as well as all the 500 maybe nodes that you have. So it's not really what you want. So this is really only for the few cases you really need I/O. And then we have a couple of instructions that let you set like state local variables and get them later. The cool thing here is that the master node can actually set a variable which can then be read by one of the remote nodes. And this is really convenient to be able to do. So your master orchestrator can actually write some variables, and before the remote nodes run their map or reduce, they will actually be able to read back the exact same variable. So these are sort of communication variables in the distributed cluster. Now, the underlying MapReduce type is just what you would expect. It takes some MapReduce options for just one isolated MapReduce run. It'll take a serialization prism again for between the mapping and the reducing stages. It'll take a mapper. It'll take a reducer. And you'll notice that essentially everything is very polymorphic. So, inputs of type A, in between key type K, in between value type V. Reducer takes that key type and value type and finally spits out B. So the whole MapReduce looks like it takes input types of A and spits out output types of B. Which is pretty much, I think, what you would most naturally expect. Okay. Anything that's too out of place so far? Otherwise, I'll show some examples, I think. Okay. So, for those of you, I guess, who may not be not so familiar with, I guess, the free monads and the operational monad, essentially, once you define this interface, you then, essentially define, just using that, this is very simple, the key instruction set that operates in your new monad. So this is pretty much all we have in Hadron. So we have a connect operator that takes the MapReduce input, output, a name, and it's just a controller unit action. We have a version of it that doesn't require an output tab, but it on the fly creates that output tab for you. So this is for cases where you don't want to create all these tab locations, but you want the framework to just give you a temporary file location. You have the set value, get value combinators, and then you have your I/O combinator. So think of it like controller is a monad in which this is all you can do. There's really nothing else you can do with it. It's just for connecting MapReduce programs. So here's, I guess, why we went through the trouble of all this free monads and the operational monad. I'm kind of losing voice here occasionally, by the way. Hopefully it'll continue working. Okay, so this is the main reason we did this in the first place. So what we want is, again, and we should probably have sort of had a diagram here, but in a MapReduce run, you have a central node that manages everything, and then you have your actual worker nodes. So you have one central node and maybe 200 worker nodes. Now, ideally what you would want to do is you want to construct a single program in the controller monad and somehow magically know how to orchestrate the whole chain of runs and on the remote nodes actually run the maps and actually run the reduces. And the nice thing that the free monad gives us is that it gives us something that we can interpret with multiple interpreters, and we have two interpreters. Our orchestrate interpreter takes a controller action, and if you remember from the previous slides, this literally is, let's say, your 7-step MapReduce program. It takes that, it takes some Hadoop environment variables. It takes a rerun strategy, which is for if the destination file already exists, should I just skip or should I delete it and overwrite it? Just something very simple. And don't worry about the state. That's just the starting state. And then it just runs it. So literally in the I/O monad. The nice thing about this is this guy intelligently runs only on the master node. So of your 200 worker nodes and the master node, so a total of 201 nodes, only the one master node will run this code path. And when this gets run, it actually figures out what's involved in running this controller action, from all the commands that it needs to issue to Hadoop, like all the central coordination it has to do, all of that stuff. It just figures it all out, and it actually ships itself as an executable to the remote nodes, which is pretty cool. It says, where am I? Okay, this is me, and then it ships itself to the nodes. And then it sort of does some intelligent tricks to get the nodes to realize that they're remote nodes and not the central organizer. So that's the orchestrate function. And then on the actual remote nodes, what runs is this part, the runMR function. It takes the same controller. So as the programmer, it's not like you design one central orchestrator and then design the actual MapReduce. You write it once. The same thing gets run on the nodes totally differently. In this case, it'll actually not do any of this stuff. It will literally actually map over the incoming data, or it will reduce the data into something. And even there, it does some intelligent things to figure out whether it's in mapping mode or in reducing mode. Because I guess the interesting thing is that all of this is just a single executable. So it's just one executable that intelligently knows whether it's in master, puppet master mode, or in mapping mode, or in reducing mode, which is all made possible by the free monad, and it's pretty cool. Okay. So I guess after doing all that, here's an example program. It does one of the simplest things possible, and if everything is still working and if our servers are up, I'll actually show you the actual run of it after this. So here's how we construct our programs. We're all in the controller monad, so we don't touch the low-level interface. We first define our input and output locations. So our input location is the test tab. We're using Amazon's S3, so it's in Soustone, Research, Hadron. We have some market data that we collected off the internet, all public data, so canvas.csv. And then it's a CSV protocol, so what that's saying is that when you see the file, when you open it as a byte string, automatically translate that to a CSV format. So that's that. Then we have an output location, which is called word count output. Again, it's a CSV file destination, so whatever we write to it will look like a nice CSV file that can be opened with whatever. Again, you give it a location, you define its protocol. Then you write the actual MapReduce program. You say, well, it's MapReduce with these options. Use the serialize prism in between mapping and reducing. Here's the mapper, here's the reducer. The mapper does something really simple. This is just conduit code in here, because if you remember, mappers are conduits, and then reducers are also conduits. So it says await forever, so just take incoming rows, essentially take the elements of the row, split it into words, concat map, I guess, or that whole thing so that it's one flat list, and then for each word in that list, yield the word itself and the number 1, so count 1. So this is our mapping state. Essentially, we're emitting ones for each word that we encounter. Then in the reduce stage, this probably can be made prettier, but it works just fine. Just fold over the incoming stream of sort of ones for each word, which gives you the total count for that word. Unless the word is nothing, as in, I guess we're done processing, just yield a map, a dictionary, that has the word and its count. So it's pretty simple. There's actually a little bug here that I have fixed on my computer. Nothing that affects the functionality, but if we do it this way, we don't actually record what the word is, but you don't have to worry about that, just a minor typo-like mistake there. So this is our MapReduce program. It's just one MapReduce step. So if you have a 7-step MapReduce, you would craft 7 of these things, and once you have all of them crafted, you would connect them, sort of, in your controller monad. And in this case, it's very simple. My app is connect the word count program, which is here, with my input, which is test app. Here's my output, word count output, and I just gave it a name, count words in canvas. Then you say main, Hadoop main, my app, preload sort of the Amazon Elastic MapReduce configuration, and if you run into your output that you ran because you ran before probably, just delete it and overwrite. So this is it. The cool thing is that you just take this, you compile it, it gives you a simple executable. Certainly there's some, okay, you have to take the code, you have to ship it over to the Hadoop node. The Hadoop node already needs to have Haskell installed on it, so it needs to be able to compile this program, sure. And we have some, custom scripts that make this process a little bit easier, but that's not the too interesting part. And then you basically just run it. So you basically say Hadron demo, and that's all you do. You don't touch anything else, no ugly, lots of configurations. And it actually starts, it figures out that it's the master node, then it says, okay, destination file exists because I was running it for a second time. It deleted the directory, got rid of it, and then it says, okay, launching Hadoop job for whatever the name we gave to it. And then it also, sort of for debugging, it gives you the Hadoop arguments. You'll notice that in the arguments, it actually sort of has this 64 character unique token that's necessary because you might be running a lot of these things, so each run really uniquely recognizes itself. And then dash file, it actually ships itself. That's the dash file part. Runs for a while, and then it says success. So just to try to show you this. All right, that's visible. So that's from a previous run. I was just testing it a few minutes ago. So I just run it. Yeah, so it just said, okay, the destination exists, I'm deleting it. Here's the actual Hadoop call, which is helpful because if for some reason this fails, you can actually copy and paste that whole sort of line, and you can also run it manually, and it will run just fine. And again, the I guess interesting thing from a Haskell design perspective is that right now this thing is running in orchestrate mode. So this is not the node, it's actually figuring out what to do and how to launch the whole job. But once it's shipped and once the binary is actually on the worker nodes, they're all going to run in the runner mode. So they'll either map over the incoming data or reduce over the incoming data, depending on in which role they are. So this actually doesn't take too long. It should finish pretty soon. And let me see if I can. If I have the ports properly forwarded. Oh, maybe I don't. Too bad. I was just going to show you, if you're familiar with Hadoop, there's a status screen for Hadoop. So as this is running, we would be seeing the status screen if that was working. Where am I? Okay, here. Yeah, and it's actually done. So success. The run concluded. I have an FTP-like program open with the destination location for that. I'll delete my previous results. So Hadoop actually ran, and the way Hadoop runs is it doesn't create one file because it runs in a distributed fashion. It'll create one file per reducer node, and this was a 3-node operation. So we have 3 servers running on Amazon right now. So I'll download that to my local. I should have it here. I'll add the CSV suffix to one of them. Okay. And I'll open it. I'll, I guess, sort it so it looks a bit better. Right, so, I mean, this was a data set that contained a mixture of numbers and words, but essentially what this is saying is that, right, I mean, the word Camilla, for example, appeared 96 times in the entire corpus of the data that we had, and it keeps going from there. But, just a simple, I guess, complete example of the whole thing actually working. Okay. As you can imagine, the way we constructed this thing was pretty inefficient. I mean, you can see that a lot of things here can be sort of pulled out, made into combinators that make this sort of thing easier. That's definitely true. We definitely developed this library to meet some deadlines and to get the work done. I have to admit that we didn't take a, we didn't sit down and think about it for 2 months and then really created the nicest design. So some of the combinators were just obvious and we needed them. So we have them, but there's definitely potential for many more. So we have, for example, something that has the ability to merge tabs intelligently. So that is essentially not a join, but kind of. Let's say you have 2 different data coming in from 2 different tabs, and you want to be able to deal with both. So you call merge tab, and now you have a new tab that gives you an either A or B, and you can do with it whatever you want. We have a MapReduce combinator that gets rid of all the conduit stuff. So if you don't like working with conduit, that's a good way to just get rid of the whole conduit mess. And then we have first by, which is sort of, if I remember correctly, it just picks the first item from each reduce key. That's helpful for deduplicating things, for example. If you want to deduplicate by day, for example, you can do a MapReduce run where your key is a day, and then you call first by, and you'll pick the first item out of each day, for example. We have a pure mapper, so all it does is it just maps incoming data and doesn't do any reduce or anything like that, so it's just a mapper, mapmr. We have one snap, which is a useful combinator in conjunction with some other things in the library where once you have your full output, it'll just take one snapshot out of it and save it somewhere for debugging purposes. And we actually have joins implemented as well. So this is what's called a mapper side join. Not to go into a lot of detail there. I think there's a lot of room for improvement on the joins, but we can actually join multiple data on some common key, which is a big thing. I mean, once you start analyzing data, joins are almost everything in this kind of work. So I guess with that, I just want to say that it did come a long way. It's very functional. I think we've used it on maybe 3 billion rows of data. I think that's our highest count for now. It ran on maybe 470 nodes or something like that. It ran just fine. It works really well. But there's a few shortcomings that we notice as we use it. For example, there's no way to compose MapReduce programs outside of the controller monad. So sometimes you just want to construct a long chain of MapReduce programs without ever caring about where your data comes from or where it goes to. You would just like to say that this is one big MapReduce program that just runs all the way through, and then at the very end you want to join data, which this we can't do right now. The controller monad, as another problem, is too strict. So, for example, you might have noticed that if I have, let's say, 20 MapReduce programs, maybe it is possible to run the first 3 sequentially, but then in parallel, the next 5 could be running, and then in parallel, maybe the remainder could be running. So you could achieve some parallelism, which we can't do. The controller monad, because of the free monad, it literally says run this, then run this, then run this, then run this. Parallelism is hard to achieve in its current form. Once you start using it, you notice it's still possible to construct incorrect programs. It's much better than its base form, but you can still make mistakes, and they get annoying when you make them. You spend a lot of time debugging, and that's not optimal. Like I mentioned, Conduit is really nice because it has a big ecosystem. You have unzippers, zippers, you have CSV converters, you have XML parsers. Michael Snowman started the Conduit library, and there's a big ecosystem around it. That's a big benefit, but I have personally observed it to have some quirks, and when you least expect it, your program is just not going to terminate, and you'll wonder, well, why? And then you'll get rid of one of the Conduit sort of chaining operations, and it'll work, which will leave you thinking, okay, that's definitely not what I expected. But I've never been able to properly debug it. So it just happens. I have no clue why it happens. You remove the chaining and it works. And it sucks when it happens. And I think there's a question around the controller interface is still not high level enough. So you still one by one construct these programs and you still run them in a certain sequence. I suppose it would be nice if we implemented some kind of relational algebra or at least some kind of a computation DSL on top of what we have, or maybe replacing what we have, so that for some simple things you can just very naturally express what you're trying to get to, and it just translates that to maybe a series of MapReduce runs. So I suppose if we do this, we get very close to what SQL does. And then like I mentioned, joins do work, but I think they need some work to make them better for multi-joins especially. So So I think that's about what we have. Thanks for listening. Hopefully it wasn't too boring for you, and I hope you find the library useful. If any of you is interested, we are very, very open to active development on it. Again, I'm admitting that our development is mostly need-driven, so if we find something we can't do, that's when we fix things. So if anyone is inclined to work on this and make it an even better Hadoop library using Haskell, we're very open to it. So thank you, and I can answer. So any questions I can? Yes, sir?
Any penalty that you pay for performance on performance?
Yeah, so performance, I'll admit that we actually never tightly measured performance. I mean, Hadoop is the kind of thing, at least for us, you just throw a few hundred machines at it and it runs in decent time. You don't notice crazy slowdowns, but our friend from the Snap group, Greg Collins, he actually looked at the code base a while back, and he definitely, for example, immediately noticed some performance opportunities. So I think they're in there. So if somebody looks at it with performance eyes, I think there's quite a bit we can squeeze out of this. But it runs still fine, like I said, over billions of rows of data. So anybody else?
You use Conduit, right?
Yes.
Why not pipes? Why not machines? There's like so many libraries that do the same thing.
Right.
Why did you choose that one?
I think two reasons. One, the original reason is that Conduit just built a whole ecosystem around it really fast. I mean, you look at Hackage, there's maybe, I'm making this up, but I think there's like 20 libraries that support the Conduit ecosystem. There's something for everything, it seems, which is why we started using Conduit elsewhere. So when the time came to design this library, we knew how to use Conduit, and because of the same reason, it did make sense. But we looked into the I/O streams library. I think it would yield a much more robust solution, but the API gets not as convenient. And I think there's potential to switch over to pipes, but somebody just has to do it and test if it's actually better. Anybody else? All right. Thank you.